Okay, off we go. So last time we were talking about parameterizations, and remember the big idea is, there's a couple of different ways to think about it. It's a way to get some algebra on the page in relation to a curve that you might be interested in, right? Depending on if it's what kind of curve it is. It might be hard to write an equation for it, or it might be hard to describe it in some other way. It may not be possible to write it as a graph, for example, of some function. So it's another way to associate algebra to a curve. So what we're going to talk about now, let's see, quick rewind. Last time we're talking about given a curve. Let's see here. Given a parameterization. So if you know the parameterization, how do you figure out what curve? That's parameterizing. We're going to turn that around backwards now, and we're going to say, suppose you know the curve already. And what you want is to find what is a parameterization of that curve. So this process of creating a parameterization is called parametrizing the curve. Okay, so there's various different methods for how to do this. This is another tools for your toolbox kind of situation. I'm going to start with my favorite parameterization technique, and that is what I call the graph parameterization. So the big idea, if your curve is a graph, now we're going to say more about what a graph is in a few days. But for now, I'm just going to say a graph is a curve in whose equation you can solve for one variable in terms of the others. Right? So here you see as what we're looking at here, I've got y written as a function of x. Okay, so if you can do that, here's the magic trick. Here's the thing that makes this technique work. Just let t be whatever your input variable is for the function whose graph you're looking at. All right, so let's see this in action. It's as simple as that, by the way. It's kind of amazing that some little quick, easily remembered single little observation will just make everything fall into your lap. So here we go with an example. Let's look at this curve right here, and y'all know that curve, right, from way back, middle school probably. And notice it's a graph. Y is viewed as a function of x. That means x is our input variable, and so my first move, per the method we just discussed, is to let x be t. And I claim we've already won. Game's over, we win, because if x is t, that basically forces y to be t squared, and check it out, we now have position as a function of a single parameter t, and that is our parameterization. Everybody see how that works? It'll always work. Any graph does have to be a graph. That's the requirement. But for any graph, that will parameterize. Okay, now here's another example. This doesn't look like a graph at first glance, because you look at that equation, it does not currently have one of the variables solved for in terms of the others, other in this case. So, but notice you can solve for x. No problem. Now we have one of the variables written as a function of the other. Doesn't have to be y. Right? There's nothing magic about alphabetical order in math. So here it's just a lot easier to solve for x, and in so doing, that means that y is our input variable. Therefore, by the rule, we're going to let y equal to t, and then again, we already win, because when y is equal to t, then this function of y becomes that same function of t. And again, parameterization. Position is a function of time. So, lovely little method. Make sure to remember this super convenient little trick right here. Let t be the input variable. Again, make sure to remember this, of course, only works for a graph, because you do have to be able to then rewrite the output variable in terms of that input variable. And it's all over. Okay. What do you think? Is everybody happy? All right. Now, here's a totally different method. Again, tools for your toolbox. In some cases, it turns out that the curve can actually be really hard to describe. We can't write an equation for it. Oh, this is actually a pretty good such example. In those cases, sometimes vector algebra can be the thing that makes all the difference. So here we go. Now there's a lot of details in this example, so you have to bear with me. It's going to take us a while to think through all these details. We have a wheel, radius A, and it's rolling to the right on the ground, which is the x-axis. You imagine that wheel just kind of rolling along. And then also we have a reflector that is attached to the sort of the rim of the wheel. And as that wheel rolls, of course, that reflector is going to be turning, but also sliding with the wheel, and it's going to make, y'all probably seen, you see, anytime it's, dusk or whatever, and you see some bicycle riding around, and there's street lights, and that reflector you can see kind of doing this little jerky, sort of scallopy kind of motion, right? Keep a lookout for that, over the next few days. So our goal then is going to be how to describe that curve algebraically. And real quick, I'll point out that if you try to do that with an equation, it's not going to be good. It's really, really hard to write an equation for that curve. It's not that it can't be done, but it's you don't want to do it that way. So it's going to turn out that it's actually pretty easy to parameterize. There are some details, and that is a little annoying, sure. But this curve, we're going to parameterize by just considering a certain moment in time, looking at the position, and thinking about how we can use vector algebra to write that position as a sum of simpler things. That's the big trick. Sometimes the whole is not the sum of the parts. Sometimes the sum of the parts is a lot easier. And this is one of those times. Okay, so in what way are we going to view this as a collection of parts? And let's see here, color choices. I'm going to understand the axle first, and then I'm going to think about this vector here that I'm calling D. And I'm going to make the observation, and you've got to look at the picture, but axle plus D gets you to P. Right? Everybody cool so far? It's going to turn out that writing down the position of the axle is going to end up being pretty straightforward. Really, it's not that big a deal. Writing a formula for that D vector, turns out it's not that big a deal. And just simply adding them together, then, let's see here, just to document, adding them together gives us what we're interested in. Oh, I forgot to hit the, there we go. So blue plus purple equals orange. Okay. All right, so let's talk details. We're going to start with the blue, start with that axle. I hope it's a relatively easy pitch that, in fact, the axle is just going in a straight line. It's horizontal. The altitude is always A. So the y-coordinate's pretty easy. The big question, and what's going to be a little tricky, is to understand the axle's x-coordinate. That's what we're going to have to do some thinking about. This argument is going to turn on a very simple physical assertion. It's just going to be a physical appeal, right? I hope this will seem reasonable. But the x-coordinate, namely how much road we've covered, how much road has touched rubber, has to equal to the amount of rubber that has touched road. You just got to think about that physically. And my suggestion is that this is what it means for the wheel not to be slipping. Right? If it was an icy road, by the way, watch out for that later this evening. If it was an icy road, then there would be slipping, and this wouldn't be the case. But on nice dry concrete, which is our assumption here, rubber has to equal road. Yeah.
So is the vector A the vector from the origin to the center of the circle?
Yeah, so I'm using here, and we'll be using the following fairly commonly, this duality, that points can be thought of as points, as locations, but they can also be understood by way of their position vectors. So the answer to your question is either. And in this case, I don't know, I find it convenient to think of A as just being a point, and point plus vector operates by how I have the picture drawn there. If you choose to think of it as a vector, then vector plus vector also works the way that we have drawn there. So basically take your pick. Does that make sense? Okay, so rubber equals road. And good news, the rubber is actually easy to understand. That's the arc of a circle. And so it's just a matter of remembering that old formula from high school geometry class. Now, before I write that down, I do want to talk about this angle. So this angle that determines that arc, I'm calling it T, you'll notice here. So this was a choice. I didn't have to do that. It was a choice. The goal, of course, is to give position as a function of time. I'm going to call that time because angles are convenient. When you know trig is going to come up, and sort of obviously trig is going to come up here, we got, whenever there's a circle, right, trig is likely to show up. And then also notice that angle T, when we start at the at x equals 0, t equals 0, and then as the wheel rolls to the right, t increases. So that happens to be a particularly convenient angle to choose to call t, and so I make that choice. Again, I emphasize it's a choice. If you want to pick a different angle for some other reasons, there's nothing really wrong with that. So suit yourself. But I think it's going to be hard to beat this for convenience. So that's my choice there. Okay, so with that said, our angle is T. Don't forget our radius is A. Right, and so high school geometry then tells us that what we're interested in. Let's see here. What we're interested in, namely the amount of rubber that has touched road, namely the amount of road that has touched rubber, namely the x-coordinate of our axle, is just radius times angle. Everybody happy? Okay. Let's see. Next, we got to get our hands on this D vector. How are we going to understand that D vector? It's a little bit scary looking because not only does it kind of rotate as the wheel rotates, but also it's kind of moving to the right constantly. And how are we going to sort of deal with the fact that it's moving? And let me remind you, when you are viewing a vector as a vector, it does not have location. So this idea that the purple arrow that we were interested in is also sort of moving along, we don't care. All we're interested in about D is the direction and the magnitude. Right? We can treat that just as a position vector, like I have it drawn here. And what I'm going to be adding it to, I'll worry about when we get around to actually adding it to something. Okay. So, easy to recall that, in terms of this angle theta, right there, D is easy to write down. Now this is a flashback to trig. Make sure you're good with your trig. Some people define sine and cosine in terms of triangles. I think that's a mistake. It's easy on the first day of trig class, but it's ultimately in the long run not as useful as thinking about sine and cosine in terms of circles, unit circle in particular. So this being a circle of radius A, we get that formula for the D vector. Which looks nice and everything, except it's not in terms of T. So what I need to do is understand how to rewrite that in terms of, let's see here, our angle T, which is like that. Right, so we've got two angles here. We've got the green angle, And we got the the red angle. And all together, oh gosh, what color have I not yet used? Well, here we go. All together, those angles add up to 3 pi over 2. And so therefore, I can solve for theta in terms of t. And having solved for theta in terms of t, let's see here, I used green for theta. Plug in that formula for theta into there. Use your angle addition formulas that you all probably saw back in high school trig class. By the way, I'm aware of the fact that a lot of high school trig classes allow you to not memorize the angle addition formulas. That's not going to work for engineering. Trig comes up all the time, and those angle addition formulas are super, super useful. If only for our purposes here in Math219, I do need y'all to know those formulas. So that is written on the content syllabus in the prerequisite discussion. So make sure you know angle addition formulas, and that allows us to rewrite this as needed in terms of t, like so. Okay, make sure to check those details. And we are basically done with this example now. I'll just remind you the big idea. Oh gosh, let me try to fit all this onto the page. Do that. Here we go. So the big idea was that the reflector, whose motion gives us the path we're interested in, is A plus D, right? So A being the axle, and D being that vector there, so blue plus purple. Well, we have a formula for blue, and we just got through writing down a formula for purple, and using that initial strategy we wrote down up there, here's our final parameterization. Notice not even all that ugly, right? It's pretty straightforward, really. And so, yeah, there were a couple little details we had to remember trig, and we had to think about vector algebra a little bit, but ultimately not so bad. And again, I claim if you try to write the equation of this curve, it's not going to work out very nicely. How we doing? Everybody see the big picture strategy here? Again, the foot in the door, the thing that made this possible is this first observation right here, that the thing I'm actually interested in is a sum of simpler things. Okay, so look out for opportunities where that might be useful. Let's see here. Here's another such opportunity. Suppose you want to parameterize a line. There is a highly standard, very commonly used method for how to do this. If you want to parameterize a line, start with a point on the line and a vector parallel to the line. Notice that characterizes the line. Any line that you want to parameterize, you're going to need to find a point. You're going to need to find a vector parallel to it. And with that done, notice that this expression right here, starting point plus t times v vector, parameterizes the line, and it does so as follows. Any point on the line is blue starting point plus some multiple of your v vector. So, nice and simple, crisp little result. Very commonly used. Make sure to memorize that construction. Make sure to understand exactly what the players are, and that's going to come up a lot. Everybody happy with that? Okay. Yeah?
Do you say like V is a unit vector here, or does it not?
It doesn't matter. It doesn't matter. That's a great question, because here's something else I should note about parameterizations. They're not unique. Right? So if you have a curve and you want to write it as a graph of a function, that function is unique. Right? There is only one function. If it exists at all, right? But you certainly will never have multiple functions whose graphs are all exactly the same curve. Parameterizations are not even close to unique. Right? There's lots and lots of parameterizations for any curve. So if you pick a unit vector, and then if your friend picks a non-unit vector, or a unit vector go in the other direction, or whatever, you'll just get different parameterizations of the same curve. Yeah, so it doesn't matter. Anybody else? Everybody's good. Okay. All right, now here's another one of these. You remember we talked about we're going to be doing a fair amount of this, unfortunately. Wouldn't it be nice if we had time to talk through everything, but we just don't. So mostly I'm going to let y'all read this page. I am going to, as usual, make a couple of comments to try to point out specifics to be on the lookout for. Here we're interested in this ellipse. And the thing is, there is an existing parameterization that we already know, namely of the unit circle, that's, it's not the same, but it's closely related. Now, I'm sure y'all remember this from high school, probably, I think that when I was in school, they called it Algebra 2. I have no idea what they call it now. But high school algebra, ellipses are just stretched out circles. Right? And in fact, you can see how much they're stretched out. So these numbers here, 3 and 2, tell you how much to stretch in the x and y directions. And so the big idea is to take your existing parameterization, and then literally just stretch correspondingly. And lo and behold, we have the parameterization for the ellipse that we were hoping for. So this idea of deforming an existing parameterization, a very useful idea, comes up in various different situations. This is a pretty good representative example. Another tool for your toolbox, a good thing to keep in mind. Make sure to think through those details. I'm also going to point out, and I know I'm in the, you read section here, but I feel the need to say a few things. Very commonly, students conflate parameterizations and equations. I think this is a real problem. Subtle distinctions are important. It is a mistake to think of these as, it's some algebra that you write down to describe the curve. It's true, but they describe the curve in really different ways. And so notice in particular, parameterizations have the feature that the points are what comes out. Parameterizations produce points on the curve. That is not what equations do. Equations do not produce anything. They do what I like to call testing, right? So if you have a point and you'd like to know whether it is or is not on your curve, that's what an equation does. You take that point, you plug it into the equation. You either get a yay or a nay. The equation either works or it doesn't. Right? So notice that they're kind of structurally, sort of strategically, totally different. So please make a conscious effort to not conflate these in your mind. They're very different constructions. By the way, eventually, of course, no surprise, we're going to be learning some calculus. Right? I know we haven't done any calculus yet. It's going to take us a couple of weeks to get to calculus. But the calculus of parameterizations is completely different from the calculus of, what you might call equations here. Completely different. So the geometric interpretations of, when you write down some calculus, what does that look like? Well, it's completely different depending on what you're looking at, a parameterization or an equation, and we're going to have a couple other options as well. So you got to make a point, and I'm going to be hitting this point again later, but you got to make a conscious effort not to conflate these kinds of constructions. And here's a nice example. I'm going to let you all just read this one, but a nice example of how we capitalize on the structural difference of these two different kinds of bits of algebra. Okay, now the following you might have seen in Math218, you might not have. I'm getting my experience and interactions with students suggest that maybe most Math218 sections don't cover this, but I think this is a really important idea. If you have a parameterization of a line in space, so this is in 3 dimensions. That's great. It's a parameterization. It's algebra on the page, right? But as we just discussed, that's a point generator. Sometimes you need a point tester. That's not it. Right? So let's suppose you have that parameterization, right? And then someone comes to you and says, hey, how about, here's a point, 1, 2, 6. Is that on this line? How would you tell if that point is on this line? And as written, you just have to start plugging in values of t and hope you get lucky, and hope that you just happen to coincidentally produce 1, 2, 6. So as written, not a good point tester. So let's think about how I can turn this into a point tester. And the idea is that if this point is on your line, if it is produced by that parameterization, then that means there will exist, don't forget that little mathematical shorthand right there, that means there exists a value of t. And then here's a little bit more mathematician shorthand, that weird looking kind of a backwards, I don't know, is that a backwards Greek epsilon or something? But anyway, that little weird-looking symbol means such that. So there has to exist some value of t that actually produces the point in question, right? So that would be one way of testing, but we don't algebraically know how to proceed there. So the clever observation is just to take this equation and solve for t. And the thing is, you're going to get 3 different answers. When you solve for t, you can solve for t in the first coordinate equation, or the second, or the third. It doesn't really change the algebra. We're just kind of moving things around. But in this form, it's so much easier to answer the question. Is there a value of t that's equal to all 3 of these things? Well, let's think about that for a second. How could there be a value of t that's equal to these 3 seemingly different things? One value of t equal to 3 different things. Only possible if those 3 different things are equal to each other. And so that's your test. If those 3 things are equal to each other, then that value that they're all equal to is the t that produces that point. And if those 3 values are not all equal to each other, then there is no value of t that produces that point. So, nice little point tester. You can just plug in. You're going to get 3 things that need to be equal instead of 2 things that need to be equal, but effectively point tester. And this is called the symmetric equations for the line. Everybody all right? Anybody see how that works? Real clever little trick there. Okay, yeah.
So if you're testing point 1, 2, 6,
Yep.
then is x 1 and then x not?
Yeah. Here, let me give you an explicit example. Let's suppose that this was 1, 2, 3, and let's suppose that this is 4, 5, 6, right? And let's suppose that the question is, let me just use some different numbers. Let me say 7, 8, 9. I'm just not feeling very creative. There we go. So if that's your scenario, right? So we're looking at the blue point and the green direction vector. Then I would need, let's see here. I would need for 7 minus 1 over 4 to equal to 8 minus 2 over 5, etc. Right? And so that's going to give you 3 different values, and you need all of them to equal, and at a quick glance, it's looking like it's already failed, right? Because those first 2 aren't even equal. If the first 2 aren't equal, they can't all be equal, right? And so right off the bat, boom, we're done. That point is not on that line. Okay. All right. Okay, moving along. Section 1.3. Now again, tough decisions and all that stuff. I think this is a pretty straight read. I am gonna make a couple of comments, but most of section 1.3, I think our best choice is not to sacrifice the really, really big need for time that we're going to have when we get to chapter 6 and 7. And instead, talk about dot products that y'all have seen before, right? That's a big thing in Math219 or any linear algebra class. So remind yourself of dot products. There may be some stuff in here that you haven't seen before. Likely candidates are components. Very, very possible you haven't seen components before, so let me say a quick word about components. The idea is that if you have a vector, W, and you want to know, okay, to what extent does that point in the direction defined by some other vector, V, right? And so I'm not interested in the magnitude of W. That's not the point, right? What I want to know is, to what extent have I moved in the V direction specifically? In the V direction is all that I care about. I couldn't care less about the extent to which I've moved perpendicular to V. I just want to know how far have we moved in the V direction. That's what the component is. It's this distance right there. That's what we call the V component of W. And the way you're going to figure this out is to notice that we have ourselves a right triangle right there, and you write down some trig and blah, blah, blah. You move stuff around, and you get a nice formula and pithy little summary. So here's your eventual formula for components. It's that dot product. Rest of the details I want y'all to look through for yourselves. And again, let me remind you, come to office hours if you have any questions about any of that you can't resolve for yourself, between yourself and your study buddies, etc. Okay. All right. Very closely related idea, the idea of a projection. Same setup. We have some vector we're interested in. We have some other vector defining a direction. And again, we're kind of interested in this. The difference is that now we're interested in that not as a scalar, but we're interested in that as a vector. That's the big difference between a component and a projection. Let me just try to clean up. There we go. So that's called the projection. And you can see it's closely related to component. Right, there's component right there. The component gives you the magnitude of that vector. And then the little tricky observation, no big deal, ultimately, is that the direction, and keep in mind that any vector, such as this projection, is just direction times magnitude, and the direction is a unit vector pointing in the V direction. So we know the direction, we know the magnitude, done. So other little details to read. Please do make a point of reading all of this. The book gives you a different take on this, kind of a pro-con sort of thing. I'm going to take just a moment to make the case for why I like mine better. Oh, whoops, wrong color. This versus this. These are equivalent, right? They'll always give you the same thing. The book's formula is what I'm going to call computationally convenient, because we're given a vector V and a vector W, and the answer is in terms of V and W that you were given in the first place. So when it comes to plug and chug, there is something kind of nice about that. But let me point out as well, there is actually something not nice about it. Ultimately, What you're interested in with both components and projections is, as with everything in this class, you're interested in ideas, right? And V, ultimately deep down, is not what we actually care about. The only reason we talk about V in the first place is because we need some way to describe a direction. And really the best way to think about a direction, the most natural way to think about a direction is a unit vector. Not an arbitrary V vector that we pulled out of a hat for no reason. Unit vectors, canonical, natural. Right? So I like my answer in terms of unit vectors because that's intrinsically natural to the question. And keep in mind that what we're interested in, we're not interested in computation particularly. I mean, a little bit, yeah, sure, a little bit, right? But computation is certainly not the point. Our goal in this course is to understand ideas and to see connections between concepts, and I think my formula does a better job with that. You can see right there in my formula, U is the direction. And you can visually confirm, again, right there in that formula, that W dot U, being a component, is the magnitude. So there's easier ideas in my formula, trade off with the easier computation perhaps in the book's formula. And again, depending on what kind of class you're taking, right, I think my formula is better. Okay, that's just for your consideration. Okay, now I did skip over one thing here, and I am going to come back and talk about this a little bit. This is a little pet peeve of mine. So be it. The book uses these two words basically interchangeably. I think that's a missed opportunity. Orthogonal is not just fancy talk for perpendicular. Right? So in fact, there are two fundamentally different ideas that are in play here. There is the geometric concept the geometric concept of there being an angle, and that angle being a certain kind of an angle, namely a right angle. Right? So this is intrinsically a geometric idea. By the way, it only applies for non-zero vectors. You can't talk about the zero vector being perpendicular to anything. It doesn't have a direction. Right? Zero doesn't point anyway. Angle is a statement about directions. Right? You've got to have two actual directions to be able to talk about the angle between those directions. So there is no such thing as perpendicular when one of the vectors is the zero vector. Now, here's the related idea, and it's a totally different thing, really. The related, well, let me leave this. That's geometric. Related idea is that sometimes the dot product is zero, and that's an algebraic idea, right? And so we've got these two different ideas. One's intrinsically geometric. The other is intrinsically algebraic. And yes, they are closely related, but they're not the same thing. And one of my little pithy points that I like is that if two things are closely related but different, it's very important to distinguish between them. You got to distinguish between two similar things to appreciate the fact that they are similar. Does that make sense? I think it's an important point, right? You can't be all excited about the fact that, hey, check this out. Perpendicular is always perpendicular. It becomes a meaningless statement. Right? You got to be able to distinguish ideas to be able to appreciate their connection. So we distinguish them by using two different words to describe these two different ideas. And I think the obvious choice is that perpendicular is the geometric idea, and orthogonal is the algebraic version. So now look, I didn't get brought up right, mathematically speaking, in terms of this. So I, despite my best efforts over a very long time, still find myself blowing it on this sometimes. So please forgive me in advance. There will be times when I will say perpendicular, but it should have been orthogonal, and vice versa. So call me out on it. Right? If you see me mess that up. Right? And y'all likewise need to be careful to try to distinguish and use these terms, distinctly, and not blur that distinction. Is that cool? Everybody happy? All right. Okay. Cool. Let's see, how are we doing on time here? Is that clock right?
Yeah.
Looks pretty good? Okay, all right. Okay, so on to section 1.4. So cross products. There's a lot to say about cross products. They are very closely connected to determinants, which I'm imagining y'all probably have seen a bunch of in your linear algebra class. Determinants are super important. It turns out they're very powerful geometric interpretations of all of these things. And they, cross products and determinants, also closely connected to another idea called right-hand order, left-hand order, and clockwise, counterclockwise. And so that's what we're going to start with. I'm going to introduce a new geometric idea, possibly new. I don't know. It depends on your 218 or 221 instructor. But here we go. So when you have a list of vectors, and I emphasize here, lists are ordered. In fact, I wrote ordered list. Technically, that is superfluous. The word list means ordered, right? So this is I wrote it here just for the sake of emphasis. But going forward, list means ordered. So when I write A followed by B, A is first in that list. This is not the same as a set or a collection, right? So that order is either clockwise or counterclockwise, by which I mean if you look at the first vector, that first vector has a direction. You look at the second vector, that second vector has a direction. And as you go from the green direction to the blue direction, you're either going counterclockwise, such as in that case, or if A were there and B were there, clockwise, such as in that case. Right, so it's a pretty easy distinction to make. When you make an ordered list of vectors, going from the first to the second naturally rotates you either one direction or the other, and that's the concept. Now, of course, there are some anomalous, annoying cases, such as this, which are neither. Right? That's neither clockwise nor counterclockwise. Likewise, if one of them is a zero vector. Likewise, if they're pointing opposite directions instead of the same direction. Right? So various different sort of neithers, all of which are linearly dependent. So nice, convenient sort of catch-all for the third case. All right. Now, y'all probably been aware of analog clocks for a long time, and so you're probably already familiar with a lot of these properties, but let's write them down anyway. If you have a counterclockwise list and you reflect, right, take a mirror image of those vectors, the result is a clockwise list. Just look at the picture. Right? No big deal. So we like to say that these are reflections of each other. These are mirror images of each other. So that's one little geometric property. Very cool. Here's another one. If you change the list, right here I had AB. You can see AB is counterclockwise. But if you change the list, if you switch the order in the list, then the result is going to change the order, right? Counterclockwise turns into clockwise. Again, not a deep point. And then lastly, I claim that it's this idea is independent of rotations. So what I mean by that is, here you can see I have a couple of vectors, and A comma B is the order. If I were to rotate everything, if I were to rotate the A vector like so, and if I were to, let's see if I can get this right, if I were to rotate correspondingly, by the same rotation, rotate the B vector, right? What was initially counterclockwise remains counterclockwise. And again, I think that's a pretty believable idea. You look at a hand-waving demonstration. If you look at my two fingers here, index finger first, middle finger second, rotating doesn't change the order, right? Clockwise stays clockwise, etc. Is that believable geometrically? Everybody buy it? Okay. All right. It turns out, believe it or not, that this idea of clockwise, counterclockwise is mathematically very naturally significant. We're going to see how in a couple of minutes. Before I show you that, I'm going to show you the three-dimensional version of this. This is a little weird, but when you have three vectors in 3 dimensions, you can't really talk about clockwise, counterclockwise anymore, right? Which direction would the clock be going there? The clock just doesn't really fit into that scenario, right? So, but there is an analogous idea, and it's called handedness. And this whole idea of handedness hinges on a particular hand gesture. So let me show you the hand gesture. I'm sorry it won't be recorded on the screen, but the hand gesture goes like this: index finger pointing parallel to your palm, the way index fingers want to point. Then your middle finger is allowed to bend toward the inside of your hand, bending the way middle fingers want to bend. This is cheating. No fair. Right? No hand yoga. Right? Okay, so middle fingers bending the way middle fingers want to bend, and then your thumb pointing the way, again, thumbs want to point. So technically I could probably force this, but no fair. So this is the hand gesture. Everybody see the hand gesture? Comes up a lot. Comes up in physics quite a bit as well, as it turns out. When you have a list, so let's look at this list here. A first, B second, C third. I'm just going to have to hand gesture this. So we're looking at, let's look at the left scenario here. The index finger, you point in the direction of the first vector. Now you see my index finger is pointing sort of in the direction that A is. You bend your middle finger in such a way that it points in the direction of that second vector. Second vector is B. Again, looking at the order from the list. So A, index finger, first vector. B, second vector, middle finger. And notice those two vectors form a plane. My thumb points on one side of that plane. And that third vector C points on the same side of the plane that my thumb does. Right? It doesn't have to be perpendicular or anything like that. It's just A and B define a plane. You need your thumb to be on the same side of the plane as that third vector. So what I have drawn there is a right-handed list. Now let's entertain for a quick second. Let's entertain this list. So let's see here. We have A that way. Okay, now I'm going to have to figure out how I can point my middle finger now in that direction. And again, no cheating, right? So in order to do that, keeping my index finger pointing in the A direction, I'm going to have to do this move. I'm going to have to turn my hand around, and now my middle finger, following the rules, can point in the second direction, and now check out my thumb. It's pointing the wrong way. Everybody see that? So there is no way to use your right hand to following the rules to produce that picture. But with my left hand is no problem. Right? So index is the first vector A, middle, second vector B, thumb points in the correct side of the plane as the third vector C. So that's a left-handed list. Does everybody see what I'm talking about there? Very geometric. This is unavoidably intrinsically geometric. And again, there's various, anomalous, exceptional cases, such as what if all three vectors are in the same plane, or what if two of the vectors are parallel to each other, what if one of the vectors is the zero vector, what if two of the vectors are the... There's various examples of cases where it's neither, and again, they are all linearly dependent. Okay. All right, nice. So looks like we're probably out of time here. So we will call it a week right there, and we'll pick up here next time. See y'all later. Have a good one.